I'm very excited to have Jon Kleinberg visiting us and give us a distinguished talk in the Distinguished Speaker Series. And yes, and I guess in many ways, Jon requires no introduction. You can tell from the room, and we actually had to change the arrangement. I've never seen this setup. Thank you to Mark or whoever I assume made the setup change. And Jon is a TISC University professor in the Department of Computer Science and Information Science at Cornell. His research focuses on the interaction of algorithms and networks, the roles they play in large-scale social and information systems, and their broader societal implications. And he is a member of the National Academy of Sciences, the National Academy of Engineering, and the American Academy of Arts and Sciences, and the American Philosophical Society. And he has many other important roles and awards. I guess I'll try to read the final part of awards. He has received MacArthur, Pankard, Simons, Sloan, and Van Nevar Bush Research Fellowships, as well as awards including the Nevelina Prize, the World Laureates Association Prize, and the ACM AAAI Allen Neville Award, and ACM Prize in Computing. I guess personally, I think every time, I guess Jon is the most insightful researcher I've talked to in many ways, and every time when I think about something for, years, and when I talk to him for half an hour, I feel like I didn't do any thinking. I need to redo all my thinking. That's kind of my experience every time when I talk with Jon, so I'm very happy to see him talking about formal model of language generation today. All right, Jon.
All right. Thanks. Yeah, thanks very much for the invitation to come speak here. Thanks, Sendhil, for the kind introduction. I often have the same feeling when I talk to you about research, so very much reciprocal. I always get a lot out of my visits to Chicago, where just so many interesting things happening in so many different departments and academic units, and just an incredibly, obviously, intellectually vibrant community, as all of you know and get to appreciate on a daily basis. I want to talk today about some work we've been doing on thinking about theoretical models of language generation as a way of trying to get some insight into the problem that large language models are trying to solve. This started out as joint work with Sendhil Mullainathan, known to many of you as a colleague at the Boot School from, I guess, circa 2016 until about 2023, and a longtime co-author of mine. And then so I'll talk some about how we sort of started this work, and then also in the second half talk about some work I've been doing on this subsequently with Fan Wei, who's a assistant professor in math at Duke who works on combinatorics and has sort of added a lot of interesting things to this whole picture. So this all started, I guess, ChatGPT, large language models, we're doing these amazing things. Sendhil and I were talking about this as we talk about many new developments in computing and just sort of brainstorming about what was going on. And I was, saying like, we've got to prove a negative result showing that these things can't do certain things. And Sendhil, who, with his sort of characteristic clarity on this, said we should actually try to prove a positive result, because what's amazing about them is what they can do, and we should really try to prove something that says, that they really have this amazing power. And he's like, also we should try to do this without probabilistic assumptions. And I'm like, well, that would kind of be strange, because LLMs at their heart are all about probabilistic assumptions. He's like, yeah, but do you think there's something you could say with no probabilistic assumptions at all? And I was like, that seems, kind of a little too worst case. And we went down that path and actually ended up getting somewhere, to our surprise, and that's what I wanted to report on you. The model itself is extremely abstract. It is not about any particular architecture or concrete model of computation. It doesn't involve the transformer. It sort of sits at some level above that. It's sort of trying to look for sort of an abstraction layer that's higher than that. That's sort of, I think, in the spirit of a lot of CS theory models, right? If you think about, like by analogy, in cryptography, it's always striking in cryptography how much mileage you can get in cryptography if you don't think about, say, the actual implementation of crypto systems, but you simply think about Alice and Bob communicating across a wire while someone's trying to listen in on their conversation, right? And it was sort of striking to us as we embarked on this that, sort of, there is no Alice and Bob in large language models. There's just like layers and layers of transformer architecture, and it's a giant mess. And it'd be sort of nice to ask, like, is there something at that abstraction level? So one thing we'll be trying to do is sort of try to find the Alice and Bob in the story who are just trying to communicate. Okay, so with all that said, as context, like, what is the problem that large language models are trying to solve? It's not actually so easy to actually state the question, right? In a probabilistic sense, I think, if you were to ask a researcher or if you were to ask the large language models themselves, they would say, we're trying to build a model that accurately assigns a conditional probability to every possible sequence of words, right? I give you a string and I'm supposed to estimate the probability of that. And then that way I can produce strings with high probability. But in some sense, and this was Sendhil's point that pulled us into this line of research, it was really our decision as modelers to add probability to this question, right? The language generation problem itself does not actually originally come with probabilities. That was our decision. The real version of the problem was, just design an algorithm that observes strings from an unknown language and eventually begins producing valid strings from a language that have never been seen before. Like, that's what you're really trying to do. And that seems too vague to be useful, but let's kind of sit with the vagueness for a while and see if we can actually do something with it. Now, in this abstract formulation, my plan here is to actually describe something that's to try to stay mathematically as precise as possible. So there's going to be a sort of simple mathematical model that tries to formalize that sentence. And so language is sort of like language that if you've taken an automata theory class or computability class, let's take that meaning of language, right? So a string is just a finite sequence of symbols, and a language is just a set of strings. All of our languages will be infinite, so it'll be a countable set of strings. You can think about all paragraphs in English as a language. Of course, it's not clear what counts as English and what doesn't, so if you want a completely well-defined example that's real, you say the language is all strings that are well-formed C programs, right? So that would pass a C compiler. And then it would say, like, can we build an algorithm that watches strings, well-formed programs from an unknown programming language pass in front of it, and after some amount of time begins producing valid programs, right? That'd be a well-defined question. Okay. Again, my point was, this seems too general to be useful, right? So Sendhil was like, yeah, I suggested this formulation. Sendhil was like, yeah, that sounds right. Let's work on that. I'm like, yeah, but see, that's not going to work because we've known for like 60 years that when you make worst-case assumptions for language learning, you can't get very far. And this actually comes from an old theorem of Mark Gold from 1967 that was sort of refined by Dana Englund. This is actually a theorem I first learned about from yesterday's speaker, Lillian Lee, from a survey she wrote in the 1990s about language learning. Even in the 1990s, this was a 30-year-old theorem. That's how old it is. So here's Mark Gold's model. This is sort of one of the oldest results in learning theory. This is 1967, so this kind of, Mark Gold didn't have access to a lot of big data sets or computers or stuff like that. You have an adversary and an algorithm, right? The adversary, the algorithm is trying to learn. The adversary represents nature, that's sort of providing signals to the algorithm. The algorithm thinks of a secret language that's known only to come from some finite representation, a countable list of, say, all finite automata or all context-free grammars or something, right? It's a secret language that comes from some representation. Actually, we don't really need the representation. Let's just say the secret language K is known to come from a countable list of candidate languages, L1, L2, L3. It's one of those. In fact, for this whole talk, the way we're going to specify languages is that the algorithm and the adversary are going to play this game of learning. There's going to be a black box that sits between them. And the black box simply takes two arguments. It takes a string W and it takes an index I. And if you ask it, is W a member of language Li, it will tell you yes or no. Okay? And that's what we mean to have a countable list of languages. Okay, they're going to play a game. And here's how the game goes. The adversary thinks of its secret language. It enumerates the strings of the language one by one. It can repeat strings if it wants. That's not so important. But it's enumerating it. So every string occurs at some point in the enumeration. All right. In each step, the algorithm is trying to learn the language, right? So it guesses an index. And it's like, I think it's L50. And then for a while, it keeps thinking it's L50. But then later, it sees something that makes it change its mind. Now I think it's L sub 200. And it guesses that for a while. Then it changes its mind again. Now I think it's L sub 5, and so forth. Okay, so in every step, it's guessing an index of a language with the goal that this should be the correct guess eventually. The algorithm wins the game if after some finite time, t star, its guess is correct forever. Right? So some t star said for all t greater than t star, lit is equal to k. And then we say it has identified k in the limit. It's identified it because it's right. It's in the limit because after some finite time we found the right answer. All right, that's the game they're playing. First of all, actually, if anyone has questions about this game, because this game is going to be kind of like key for the whole thing. So, game make sense? It's good.
Can the condition wi in li, can that condition on context, can that be true or false depending on history?
So at the moment, no. I'm going to add prompting to this. So you could view this as currently as like an unprompted model. So basically, you put in a string and out comes yes or no. So like, is this a valid C program? Is it a valid Python program? Is this a valid paragraph of English? I just say yes or no.
Is there any constraint on the adversary? Because a stubborn adversary can just output the same string ad infinitum, and you have an infinite t, right?
So a couple of constraints on the algorithm. One constraint is it must eventually say the whole language. So it's an infinite language. So it can't say the same thing over and over because there must, so what does it mean to enumerate the whole language? It's an infinite language. It says for every string in the language, there exists a time t such that the algorithm said that string at time t. And so that's the requirement. The other constraint, which will turn out to be a major constraint on the adversary, is that the list of candidates is countable. Right? There are uncountably many possible languages, but we've agreed it's going to be a countable list. Now, that's reasonable because, again, we're imagining that this is a secret context-free grammar or a secret finite automaton. A secret, it's something that's the whole notion of language as opposed to just set of strings, is that a language has a property that there's some finite size object that produces it. And there are only countably many finite sized objects, so it's reasonable if there's a countable list of candidates. So that's other questions about that? Right, so there's going to be this balancing act going on because these are infinite objects. The true language is infinite, the algorithm is going to speak for infinitely long, the algorithm is going to guess for infinitely long, but then something's have to happen after a finite time. After a finite time, you have to be correct forever. And that's kind of the constraint going on, right? I have to be, in finite time, I have to make a correct assertion about this infinite size object, like English, or the set of all C programs. Okay. So, why did Mark Gold make up this model? I mean, it's 1967. He's at the Rand Corporation. They have a few computers. They're not really doing a lot of natural language processing in 1967 at the Rand Corporation. He was actually partly motivated by language learning in infants, actually. Because he was like, think about a 6-month-old infant lying in its crib, listening to its parents speak their native language. Okay? There's some serious constraints on what a 6-month-old can do if it's trying to learn language. One, yes, the parents make grammatical stumbles here and there, but they don't speak gibberish. So basically, the infant is only hearing positive examples from the language. You're not really seeing a lot of negative examples. Second, the 6-month-old, although they're learning a lot of language, cannot yet verbalize. Right? I'm not asking how a 2-year-old learns language. I'm asking how a 6-month-old learns language. They can't really verbalize, so they can't ask if their guess about the language is correct because they can't verbalize. They also can't do active learning. They can't babble a sentence and have their parent go, no, that's right, or yes, no, that's wrong, or yes, that's right. At age 18 months they could do that, but not at 6 months. And yet, by 6 months, despite this apparently huge set of constraints, they're learning a lot of language. So what's going on? That seems to be one of the challenges. And particularly, with this in mind, the main thing to emerge from this line of work was so-called Gold's theorem, that there is no algorithm that can achieve language identification in the limit, even for very simple collections. Like even if L1, L2, L3 were all regular languages, right, produced by a finite automaton, or even just like simple cyclic automata, like super simple things, the answer is no. For any algorithm, the adversary can choose a language and get the algorithm to make infinitely many mistakes. Okay. And so in some sense, this line of research was over almost as soon as it began. Like, this is just way too general a model. It's way too worst case. We can't get anywhere. And then 10 years later, Dana Engelin in 1979, in a paper at Stock 79, came along and actually characterized the collections of languages for which you can identify the limit. It's very, very simple languages. It's sort of, to a first approximation, it's kind of like pattern expansion languages. Like I tell you, it's all strings of the form 0, x, 1, y, 0, where you can put anything you want for x, anything you want for y. That's basically it. Okay. Actually, her exact characterization, it's worth saying, because we'll come back to this. This was Dana Engelin's condition. When can I identify a collection of languages in the limit? It's if each language, Li, has a so-called telltale set. a finite subset, Ti, such that for any proper subset of the language that's in the collection, the telltale is not a subset of that subset. Okay? So here's Li, it has a telltale, and that telltale is enough to distinguish it from every subset of Li that's in the collection. Right, so the picture is this. Here's Li, here's any subset Lj that's in the collection, and Ti sits out of it, pokes out of it. And that's necessary and sufficient for being able to identify the limit. It's very hard to achieve that. Regular languages don't have that. So. All right, I'll come back to that. So there it is. Mark Gold asked a question. It's impossible, even in very simple special cases. Dana Engelman has this nice characterization. The end. And that's why, presumably, we have to move on to probabilistic assumptions, because, and so all of language learning moves on to probabilistic assumptions. Fine. But Sendhil and I were thinking about this, and we're like, before we give up completely, it's worth noticing one important thing. This was not the question we were actually asking. We weren't asking about identifying the language. We were asking about generating from the language, right? What was the spec? Design an algorithm that eventually begins producing valid strings from the language that have never been seen before. It doesn't say eventually figures out what the language is. That wasn't the spec. It just eventually begins producing from the language. Now, even intuitively, these two things feel different. Let's go back to the 6-month-old lying in their crib, listening to their parents speak their native language. That 6-month-old becomes a fluent 5-year-old eventually. But if you were to start quizzing that 5-year-old on corner cases of English grammar, they're probably not going to get that right. Right? Even adults can't really litigate all the edge cases of grammar in their native language. Any more that when you watch a bunch of C programs pass by you in your intro programming class, you eventually learn to program in C, you don't actually know the C programming language. You know how to write programs in C, right? You go for a super hard coding interview, and they ask you whether this nested double null pointer dereference will compile. You might not know. I don't know. That's like some weird edge case, right? You haven't actually learned the exact specification of the C language. You know how to generate it. Generating just requires that you find a big, safe subset in the middle of the language, and you know how to produce from it. And you don't really go near the dangerous perimeter of the language where you don't really understand what's going on. That's generation. So what about generation? This turned out to be, even though we were now into the era of ChatGPT, it turned out nobody really asked this version of the question. So let's ask it. Let's go back to Mark Gold's game from 1967 and just change the game just a little bit. Here's the new game. Again, adversary and algorithm. The adversary starts out the same. Adversary thinks of a secret language K, known to be one of L1, L2, L3, and so forth. Adversary enumerates the strings one by one, subject to all the caveats we were just discussing. One extra little piece of notation. Up to time t, the adversary has enumerated a set S sub t. That's like the training data, basically. Right? Okay. The new goal for the algorithm is not to guess the language. It's to output strings from the language. Okay, so this is the new part. In each step t, the algorithm outputs a string A sub t that should come from the true language minus what's... I mean, you can't just repeat the training data. That wouldn't impress anybody, right? We want to create genuinely new things that genuinely come from the language. Okay. And again, as before, we have all the 6-month-old constraints, no negative examples, no feedback on right or wrong, and so forth. And the algorithm wins the game if after some finite time, t star, every string it says is an unseen string from the language. Okay. And then, to paraphrase Mark Gold, we'll say it has generated from K in the limit. Okay, so we got to this question.
Excuse me, just to make sure, so is AT then an ST plus 1? Or can I win by just producing the same AT forever?
Oh yeah, can I produce the same AT forever? So if you want, we could require you always have to produce a new one. That'd be fine. In a way, you're going to have to produce an infinite set of them. Why is that? Say you picked an AT and you're like, I really like this one, I'm just going to keep saying it. The adversary must enumerate the whole language, which means eventually it will say AT at some point, at which point it will kick you off of AT onto some new AT prime. And eventually it will say that one and kick you off that one. So even this spec forces you, even if you try to repeat as much as possible, you will eventually output an infinite subset. Yeah. Other questions about it? So this is like game 2, so definitely important we get game 2. We're going to talk about that one even more than game 1. We're good with that? Okay. Yeah, so that's the game. So we got to this game, and we were sort of like, oh, this is interesting. Let's go back to Dana Engelman's characterization. Oh, yeah, question.
So are concatenations allowed?
Concatenations?
Yeah.
Only if they're in the language. So this language K might be closed under concatenation, might not.
But for any such language, I can easily achieve this goal, right?
Oh, you mean if the language has the property that repetitions are okay, then yeah. So, for example, if we happen to be lucky enough that all of our languages have the property that if A is in the language, then A to the K is in a language, then A to the J for some power, then I can always just keep concatenating, yeah. But we may not be that lucky. Right, exactly. Yeah, see, it's a sign of how badly I would do in coding interviews. Like, I don't think if I take an arbitrary C program and glue the same text, I don't think that would necessarily compile. So it would have two mains, it would have a lot of problems. Yeah, it's not a given if I concatenate the same string again. Yeah, okay, so this is the game, generation of the limit. Other questions about this game? This game's very important. This is the game we're going to play for the rest of the talk. Okay. So yeah, we were like, okay, let's go back to data angulance characterization. Like, generation feels more tractable. So presumably it's a bigger collection of languages that allows for generation limit. So what is that collection? Can we like prove a new version of angulance characterization? That would be kind of cool. And so step one, I kind of set out to find a single example of a language family where you could not, the algorithm could not succeed in generating the limit. Right? A single collection where the adversary wins the game. And it was sort of, for a few months, it was this confounding experience. I could not find a single example where the algorithm could be forced to lose. And the examples got more and more arcane. But in the end, the reason I couldn't was because of the following theorem, which is there's actually an algorithm with the property that for every countable collection of languages, and any adversary who enumerates one of them, the algorithm will generate from this language in the limit. Right? So it's not about slightly broadening data angulance characterization. It's that every collection allows for generation. Generation is just way, way more tractable. You can do it with basically, and so this theorem was surprising to us because it's sort of an assumption-free theorem. I've told you the whole game. It's a worst-case game. And yet, there's an algorithm that can generate in the limit. And it does mean that, yes, there really is an algorithm out there that if I say I've made up a new grammar for a programming language and I'm going to start feeding programs to it, after a finite time, it will eventually begin outputting valid programs in that grammar that I just made up. Like, that's actually true. Now, obviously, by Gold's theorem, this is going to be a game that the algorithm wins without ever knowing how or when it won the game. It's going to keep saying strings, and after some magical time that it doesn't even know when that came, it will be entirely correct. But Gold's theorem tells us it's never going to be like it can sit back and say, oh, now I know what the language is, because that's impossible. It's just generated. Okay, so my goal in the first, we're kind of 1/3 into the talk, my goal in the second 1/3 of the talk is to actually prove this theorem for you. I can give you basically the whole proof. And then I'll talk about some extensions that we've done since then. Okay, so a key point in trying to prove this theorem, which came as a surprise to us. So first of all, as you're observing, it's enough the algorithm outputs an infinite subset of k. If it can find an infinite subset of k and just do that, it's going to be good. Again, I should point out, this is unprompted generation, right? No one's giving this thing a prompt, it just has to right? This is like the language of all haiku poems. It just says, I'm going to show you examples of haikus, and eventually you'll figure out what's going on and you'll output haikus, right? But once we have the algorithm, it'll turn out it's super easy to add prompts. And so whatever works here with one extra slide will work with prompting. The real thing going on here is that somehow there's this tension. Any algorithm for generation is managing a tension between two things that you might call validity and breadth. Validity says all the strings you say must be valid. And breadth says you must output an infinite subset. So you must actually be expressive and say a lot of things. Right? You can't just have one hard-coded haiku poem that you just keep saying over and over. And so what's going on is the algorithm's going to have to manage that tension. Right? At one extreme, the sort of extreme of a failure of validity we often call hallucination. Right? That it's making up stuff that's not valid. A failure of breadth we sometimes call mode collapse. Right? We're collapsing down to a very constrained subset, and that's all it's going to say. And so it's going to have to sort of balance on that knife edge between these two things. Okay. So actually, in a longer version of this talk where I wanted to cover less ground, there's a lot of intuition we could try building up as to approaches that don't work. There's like a lot of approaches that don't work for this. And out of those emerges an algorithm that actually does work. I'll just show you one approach that doesn't work, because it's the one that kind of gets you the most on the path toward doing something here. Here's a strategy that does not work, but is tempting. So again, the one thing that we really have going for us is countability. It's a countable family of language. Like, when I say this problem has almost no structure because it's just an arbitrary collection of languages, that's true, but it is a countable collection of languages. And that puts more structure than you would think. So let's use countability in the following sense. My candidates are L1 or L2 or L3 or L4 or something. So I could say, let's just start with the hypothesis that the true language is L1. I'm just going to act like that's the answer until the adversary comes along and proves me wrong. So as long as the sample comes from L1, I could say that. We'll say in that case, L1 is consistent with the sample list. As long as L1 is consistent, what I'm going to do is at every step just output a string from L1. That's unseen. How do I do that using this little black box I have in front of me? Well, I know that L1 is infinite and ST is finite. So I start at the last string of ST, and I just start asking the black box about membership in L1 for longer and longer strings until I just crash into one of them, because it's an infinite set, so I'll get to it eventually. And I'll output that one. If I ever get to a point where L1 becomes inconsistent, I just move on to L2 and continue from there. Now, there's a lot to like about this algorithm. In fact, so much so that you can almost imagine a sort of, in the end, wrong proof that this algorithm actually works. And the wrong proof would look like this. If I'm currently at Li, right, I'm making my way through the languages. If I'm currently at Li, and it's not K, then the adversary is enumerating all of K, so it'll eventually reveal the contrast between Li and K. And I'll move on from Li to Li plus 1. Now, the nice thing is that K is in this collection. It's equal to Lz for some z. And so I will eventually march my way until I get to Lz. It's out there somewhere. And then I'll never move on, because the adversary is enumerating Lz. It can never prove me wrong. And so I'll enumerate from Lz forever, and I generate the limit. And it sort of has the structure you sort of felt like a solution would have to have, because the adversary wins without ever knowing when it has won. When it gets to Lz, it doesn't know that this is the place it's going to stop forever. It just happens to be, in retrospect, the place that it never moved on from. And so, great, you know, it solved the problem, right? It doesn't know quite when that's going to happen, but it's inexorably getting there. It's going to. So, yeah.
It can't be correct, right? Because it is violating the cold theorem.
Right. The problem, we sort of know this proof can't work because I could have written the same thing for identification, not generation. I could have said my guess is I, and eventually I'll get to LZ and I'll guess Z and I'll guess Z forever. But we know by Gold's theorem, not only does this algorithm not work, no algorithm works. So something is wrong here. This proof is not correct in a sort of deep way, right? It's not superficially fixable or it would contradict Gold's theorem. So what's going on, right? What is wrong with this proof? Yeah.
So in our black box access, do we see a new thing, or it may show us some old thing from that language?
It could show us old ones, but it has to eventually show a new one. So it can't show us old ones forever.
But then, like, the requirement was like we tell something from that language from some time t forward always. But if the black box doesn't give us something new, maybe we don't have anything new to tell.
There is a worry about that, yeah. Although the hope would be that I'm going to see a big enough sample, like even if the black box isn't giving me new things, I can generate new things, right? Like if the answer were L1, I'm going to generate new things from L1, even if the black box isn't showing me. Yeah. But it is true, right? This lack of negative evidence, the problem is this first bullet point. I will not eventually learn that L1 is wrong. Here's the problem. Before I get to LZ, imagine LZ is a very thin language, right? It's, all the powers of 4. But before I ever get to LZ, I get to a superset of LZ, right? There's some LI that comes before it that's a bigger language. Again, I'm going to misuse the words big and small for the rest of this talk. These are all countably infinite sets, so they all have the same cardinality. But obviously, one can be a subset of another one. So, okay, so I can have this sort of denser language that comes before. Now, when I get to that Li is a superset of LZ, and I never get negative examples. So nothing will ever come along to show me that Li is not the right answer. For example, Li might be the set of all strings. If it's a set of all strings, then everything I see is consistent with Li. Because remember, we're operating under the 6-month-old infinite constraint. You only hear positive examples. So, I hear a bunch of powers of 2 or whatever, and I'm like, yeah, well, that's in the set of all strings. So I'll never move on from that. Okay, and as Ron pointed out, we can't really get around this or we would have solved that information. So this was a nice idea, but it doesn't really work in a deep way. And it points out how precarious the situation is, because we want to generate the limit. Okay, so we'd like a strategy that iterates down this countable list. It gets to a language Li, and it sits around for a while, generating from Li. It's like, this is working pretty well. I'm kind of happy with how this is going. I'm never seeing examples that prove Li is wrong. Can't I just stay here forever? And the answer is no, because Li might be too big a language, and I'm going to infinitely often say invalid strings. That's just not going to work. So I have to move on, even when things look good. But if I move on when things look good, then when I get to LZ, which is actually the right answer, I have to move on. Because I don't know LZ is the right answer. So no matter where I am, I can't sit still. I have to keep moving on. And the problem is, once I've drifted by LZ, the whole point of this argument is lost. The only reason we made this argument was that when you got to LZ, you finally had the sanctuary. If I have to move on from the sanctuary, I'm just drifting out to the right down this list forever. And what good is that? That's kind of the problem, right? Okay, so here's another version of this picture. We can imagine, each of the languages is a bit vector, just showing like what's in the language. So I have like, I have L1 has string 1, string 3, string 5, 7, 11, 12, so forth. Okay, and then the next one is 1 and 5. L5 is the right answer. This is the infamous language that has everything, which is going to act like a giant filter that catches you when you get to here, and so forth. Okay. All right, and so and just strings come along. U12 comes along. It's consistent with all the first 7. U9 comes along and wipes out L1, right, and so forth. Okay. All right, so that's the idea. Now, what would be useful here is if I could find like a minimal language, right? Like let's say a minimally consistent language would be one, and a language L that's consistent with ST, and there's no consistent, where are we here? There we are. And there's no consistent L prime that's a proper subset of it, right? It's like minimal and consistent. That would be great, because if I generate from a minimal language, then it's contained in every consistent language. So anything I say here is safe with respect to everything, right? Because if I can generate from a minimal consistent language, then the true language is also consistent, so this thing's a subset of it. And you can always safely generate from a subset, right? So, and in some sense, if you go all the way back to England's condition, that is effectively what her condition was saying. That you will eventually, after a finite time, get to a point where there is a unique minimal language consistent with what you've seen, and you can just make progress from there. Okay. But of course, with these countably infinite sets, there may be no minimal consistent. I could have an infinite descending chain of languages, right? Because with countable sets, I could say, the set of all integers greater than 2 is a subset of the set of all integers greater than 1. The set of all integers greater than 3 is a subset of the set of all integers greater than 2. And I can just go out. I can just regress forever on these countably infinite sets. I can form this infinite descending chain of subsets. So I'm not going to find a minimal set. Okay, so this is our situation. We can't stay at the language K when we get to it because we don't know it's the language K. We have to keep drifting out to the right. That might be okay if we get to a minimal set, but there are no minimal sets, so that's not going to stop us. So we're drifting out to the right. There are no minimal sets. What do we do? And so you try out different definitions. You sort of play with different things. And eventually you stumble across a definition that's extremely useful. And once you have that definition, the whole problem just kind of cracks open and everything starts working. Okay? And so let me show you that definition. Let me show you how the proof finishes from there. Here's the definition. We'll say a set L sub n is critical at step t, first of all, if it's consistent, right, with everything. And secondly, it's minimal in a weak sense, which is that if Li is a consistent language that comes before it, then Ln is a subset of it. Okay, so it's minimal if I look to the left. Again, think about we're reading this countable list of languages from left to right. So if I look leftward, I look back toward the beginning of the list. And if I look rightward, I look out into the infinite horizon where there's an infinite sequence of languages out in front. Okay? So a language is critical if it is consistent and minimal among all consistent languages up to it. It's like a pinch point. Everything kind of pinches through it, because if you look at it and you look back to your left to the beginning, it's minimal over all this. Okay? So for example, here's L5. Is L5 critical right now? No, it's not. It's not critical right now because L4 is consistent, but L5 is not a subset of it. You notice that. So there is at least one critical language. The very first consistent language must be critical because vacuously nothing before it is even consistent. But the true language initially may not be critical. L5 is not a subset of L4. It's not initially critical. I want to argue, though, L5 is going to become critical. Why is that? Well, because the adversary has to enumerate all of L5. It's the true language. So it will eventually enumerate string 5 here and wipe out L4. That has to happen, right? Because L5 is not a subset of L4. So L5 has something L4 doesn't. And the moment will come when that string gets uttered, and then L4 is gone. And that actually is a proof, or becomes a proof, that the true language LZ will eventually become critical. There's some step, call it T+. I don't know when it's coming, but it will eventually come. After which, LZ is critical forever. And the proof is simply, consider every earlier language. It's this argument made more general. Consider every earlier language that LZ is not a subset of. That earlier language LZ must have something that earlier language doesn't. The adversary must eventually enumerate that something and wipe out that language. There are only finitely many, only n-1 languages before LZ. Each of those has some time at which it gets detonated. And so take the max of all those times, and by then all those are gone. And all that's left is things that LZ is a subset of. So it is now minimal among all consistent languages before it. It becomes this pinch point. Now, once you have this pinch point, you have enormous amount of power. Right? This is a very useful object to have your hands on. Because now, in one slide, I can give you the algorithm that will generate in the limit. Okay? We can just wrap everything up from here. Here's how this works. So here is the algorithm generating the limit. Okay, so in step T, we're going to consider only languages L1 to LT. We're going to look over wider and wider windows as time goes on, but always a finite window. In this window, let's look for critical languages. And let's take the rightmost critical language. Okay, so let's say L sub NT. NT is the highest index of any critical language up to T. And the algorithm is simply generate a new string from LNT. That's the algorithm. Find the rightmost critical language among the first T, generate from it. I want to claim this generates in the limit. Well, so for that I have to tell you there's some time after which I'm going to succeed forever. What is that time? Well, it's the max of two things. One, the time has to be large enough that LZ is in the set I'm considering. So T has to become bigger than Z, so that LZ is in my set of canons. Second, there was this magical time T plus I mentioned last time, after which LZ is critical. So T starts to be bigger than that also. So LZ is now critical. So it's in my window and it's critical. I'm generating from the rightmost critical language. LZ is one of the critical languages. So this rightmost critical language is a subset of LZ, because it's a subset of every consistent language. So I found something that's thinner than LZ. It's a subset of LZ. And I can always generate from a subset of LZ and be valid. Okay? So from then on, I'm generating in the limit. And that's actually, right, so once you have this definition of critical, everything just starts working. Great. Okay, so first of all, questions about this. Okay, this is sort of, we're now at the 2/3 point, yeah.
Define some sort of like equivalence relationship between two languages. If one is subset of the other one, they're going to be somehow equivalent. Is it fair to say that this is actually detecting the equivalence class of the ground-truth language?
I mean, I would think of that more as like a partial order than an equivalence relation, right? Because it's by subset, right? So you're saying like equivalence like in...
Like things that are nested are just going to be in one class, and this algorithm is basically finding that class somehow.
Yeah, although what I realize is like a tree, because there are, we're going to use this in the final 1/3 of the talk. There's like a bunch of things below that are subsets of LZ, and they may not be mutually comparable. So out of all of the sort of tree of things below it, it's picked an infinite branch down that tree, and it's following that. But it is the right picture that what this is doing is this kind of infinite regress out to infinity, where it's like it's going along these thinner and thinner critical languages, right? It's a kind of controlled mode collapse that's going on here, and that's sort of what's happening here, right? It's becoming more and more cautious in what it's willing to say, and eventually it's going to be so cautious it's inside the true language. It has no idea when that happens. Yes. Other questions about? And so that's the picture that we sort of want to play with, of this infinite regress up to infinity. Yeah.
In the limit, LNT is becoming thinner and thinner, and that doesn't conflict with the goal of being able to generate infinitely valid sentences.
Yeah, because it's always an infinite set. Like, again, as a sort of thought experiment, imagine I said, in step T, I'm going to only generate numbers bigger than T. Right, that's my allowed set. Just thought experiment. Those sets are becoming, quote, thinner and thinner because every single one's a subset of the previous one. And you're like, but I'm going to run out of numbers. I won't. In every step T, I still have an infinite set of numbers out in front of me. It's just that they are, so you can have this infinite descending chain of subsets that never exhausts themselves. Yeah. That's what's going on. Yeah, other, okay. let me talk about a couple. Okay, so I'm going to talk about a few things now, and then jump to sort of the stuff that Fan Wei I've been doing for the final 15 minutes of talk. First of all, the algorithm is actually achieving something a little stronger than we set out to. We wanted what you might call element-based generation. I should always output a new string in the language. It actually did something maybe stronger, which is, let's call it index-based generation. It's actually guessing the index of a language. And it has the property, right, Mark Gold required that eventually LIT equals K. What this is guaranteeing is that eventually LIT is a subset of K. And that one little change is what makes this whole thing tractable. And that's what this algorithm is doing. Let me tell you about 4 things in increasing order of detail. The first one is the least detail. It's just this one bullet point. The algorithm, as I told you, is not, strictly speaking, thus far, an algorithm. In the sense that an algorithm has to run in like computational steps on a Turing machine with access to this black box. The problem is in this step, where it says this is a critical language. To know if something's a critical language, I have to solve subset queries. I have to go, is this language a subset of that language? Which is not something I can do in a finite number of computational steps. So I actually have to do a bunch more work to actually turn this into an algorithm that runs in real steps on a Turing machine. I'll skip that part, but in the paper we actually get that to work. But it's much easier. In a way, that's almost a secondary thing. Like the whole literature on Gold's theorem was never about computability. Right? The reason Gold's theorem is a negative result is not because Turing machines can't do it. Even if you have the power to solve arbitrarily hard problems, the halting problem, whatever, your problem is not that. Your problem is you don't know what the adversary is thinking of, and it's still impossible. So the whole literature on this tends not to worry about computability, but instead worry about the inscrutability of the adversary. And so I too will not worry about it, but we can turn this into an algorithm if we want to. When we talk about prompted generation, so one way to think about prompted generation is that the adversary shows you training data in every step. In every step, it also shows you a prompt. So it says, let's say the adversary gives you P sub t, and the algorithm must output a completion C sub t so that PT followed by CT is in the language. Right? I say you must complete this to a valid C program. It turns out if you think about it, the algorithm I just gave you solves that problem also. Because I find the last critical language, I go look for a completion of the prompt, and when I find a completion of the prompt, I output it. If I have Oracle access to this language, if I discover that this language, if I can look at this language and have Oracle access to it, if it has no completion of this prompt, I know it's actually not consistent anymore, and I move back to the previous critical language. And so this algorithm effectively solves the prompted version also. Okay. A little bit about finite collections. I said we have an infinite collection of languages. It's interesting to ask about finite collections of languages, right? For example, I tell you, I promise this is a regular language produced by an automaton with at most n states. This is a context free language produced by a grammar with at most n productions, right? So this could be a big finite collection. Those are big finite collections, but it's finite. If you go back to Engeland's characterization, finite collections, you can actually solve identification in the limit. So it's actually a much more tractable situation. So if you can solve identification limit, what more could we ask for in the finite case? Well, there's one thing you can't do in the identification problem that's kind of important, which is I can't show you the collection and ask for an a priori bound on how long it will take you to solve identification. Like you would like to be able to look at the collection and say, I promise you that within 1 million steps, if you give me 1 million training examples, I will solve identification. That can't be done. Here's a simple reason why not. Imagine you promise to have done identification within 1 million steps. I say, okay, language 1 is all strings, and language 2 is all even-length strings. Okay? What am I going to do? I'm going to show you 1 million even-length strings and say, okay, what language am I thinking of? Now the problem is, if you say L2, I say, oh, the million first string is odd. You're wrong. It was L1. So you can't guess L2. But obviously you can't guess L1, right? You can't see 1 million even-length strings to guess L1 because maybe it was all even-length strings and it was L2. So there's no a priori bound I can give you on when I will be right. And yet, despite that, I can do identification to limit here. Because what's the algorithm? Guess L2 until you see an odd-length string, and then switch to L1. There are two cases. Either you never see an odd-length string, in which case the answer was L2 and you were right the whole time. Or the adversary is forced to enumerate the whole language, so they will eventually be forced at some finite time to say an odd-length string, and then you switch. And then you're correct after a finite time. So you will win. You just don't know when you will win.
Excuse me. I'm missing something because this sounds very passive. Why can't I actively choose a query?
Oh,
and
yeah.
separate these?
So this was the assumption from the beginning, and this was the 6-month-old infant assumption
Oh,
that Mark Gold
okay.
made.
Okay.
You just sit there passively consuming. Everything gets easier if you can ask active queries. And so, right, so if you create a model with super hard constraints, for Mark Gold proving a negative result, it's sort of like, great, you create an impossible problem and you show it's impossible. I feel like for generation, it's all the more surprising. Right? We're succeeding at generating a limit despite the fact that we can never ask an active query and we never see a negative example. And despite that, we can generate a limit somehow. Yeah. So for the finite collections, this is an extra thing you can do with generation. For every collection, you can actually inspect the collection up front and announce a bound, T of C, right? The collection is C, T of C. Say, I promise within T of C steps, I will be successfully generating from the language. Okay. And so I can actually put a timer on this, regardless of how the adversary chooses to enumerate. In this case, actually, I mean, this example is so simple for generation, I don't really need to do anything, because this is just one subset of another, right? So if I want to solve this one, I can do it in 0 steps. I just always output even length strings. That's in both languages, so I know that'll work. So this is not a particularly hard test case for generation. I'm not going to talk about the proof of this, but the proof actually uses an interesting extra idea that wasn't there with the infinite collections to get this finite bound. And the interesting extra idea is this thing I'll call closure. So the proof of this thing, which I won't give you, uses this thing called the closure operation, which is, given the sample S, you've seen ST so far, consider the intersection of all languages in the collection that contain ST. Let's call that the closure of the set. Right? I mean, closure is a mathematical object that we're very familiar with from all computers, right? Like, the convex hull of a set of points is the intersection of all convex sets that contain that finite set. And that's the convex hull. Right? The subgroup generated by a set of elements, I say this somewhat hesitantly with a bunch of group theorists in the audience, is the intersection of all subgroups that contain these elements, right? That's subgroup generated. So closure is a thing that we understand, right? It's like I take the thing and I look at the intersection of all the valid things that are in that. And so if I could find, if the closure contained more than just S, I would be all set. Because I could say something in the closure. Because it's in every consistent language. And so it's a safe thing to say. So it's almost like the closure is the little pieces of lint that adhere to the set S that I can't get rid of, right? Once I have S, I inevitably have these other things, and I can save it. And if you think about it, closure is a great way to think about generation when it works. Because imagine, thought experiment again, not our problem, not language generation, but imagine a different generation problem. I said, I'm an adversary, and I'm thinking of a secret convex set in the plane. I want you to guess what it is. I'm going to show you points. Here they are. Okay, what's my convex set? You're like, this is hopeless. I mean, it could be any convex set. How could I possibly get this right? And that's true. That's impossible. What if instead I said, I'm showing you points. I want you to generate from my secret convex set. That's no problem. Once I show you two points, I can generate from that whole line segment in between. Right? And that's an infinite set, so you'll never run out of points to generate. Right? So once you have closure working, like generation becomes much easier. The reason we didn't solve the problem this way in the beginning is that if I have a countable collection of candidates, closure is a dead end. Because I can easily create instances where I give you the sample, and the closure of the sample is just the sample. There is no extra element that's implied by that sample. And so there's nothing I can be sure that I'm able to say. And that's sort of why we had to embark on a much more complicated version that involved, critical sets and this infinite descending chains. Okay. Last thing, let's talk about mode collapse. Because this whole thing was doing this controlled regress to thinner and thinner languages. And so it was sort of almost the antithesis of breadth. Right? If I want to generate with breadth, the solution we had was not really doing very well here. So this was a topic that a bunch of people became interested in after our paper, and there's a number of follow-ups. Nice papers by Charkar and Pavaraju, by Kalabasas, Marocha, and Valakas, as well as the work with Fan Wei that I'll talk about. There's actually a nice one of the tutorials at Colt 2025 was about the follow-ups from this paper, and so if you want to see 3 hours of video on this, it's very, very nice material that they have there. We're going to talk about breadth. Like, I want to generate a lot of this language. And how am I going to quantify that? Well, I can look at the true language. I can look at what the algorithm generates. Right? The algorithm generates a subset of it. And I can look at this number f of n. F of n will be the fraction of the first n strings that show up in the output of the language. And that's breadth. Okay, now, and I want to look at this as it goes to infinity. And I would like to say that in the limit I'm generating a positive fraction of the whole language. That'd be kind of a nice thing to be able to say. So I'd like the limit of f of n to be positive and not 0. The algorithm I've shown you so far essentially has this f of n going towards 0 as it goes to thinner and thinner sets. I would like it to be positive. Now, f of n might bounce around, so it may not have a limit, but it has a lim sup and a lim inf, right? The largest number it approaches infinitely often, the smallest number approaches infinitely. Okay. Now, this is tricky. Like, we would like positive density. Okay, so that's going to be the last task that we set ourselves in this talk. Generating with positive density. This is not so easy to do, because the whole solution we built is really working against that. Right? Because, well, what's going on here? We got to the true language, but we couldn't stop. We went to later and later critical languages, and they got thinner and thinner and thinner, and they kind of go out to infinity. Right? So we sort of, in a way, started with hallucination. There was a moment when we had the right answer. We just didn't know we had the right answer. We didn't know to stop there. And so we kept going, and then we move on to mode collapse as we just keep going out here. In a way, when I was thinking about sort of the intuition for this, there's sort of an interesting parallel with the sort of to how people acquire the vernacular in new communities. So there's this striking work that my colleague at Cornell, Christian Dinescu, Nicholas Gumizel, did with some co-authors at Stanford about how people pick up the vernacular in a new online community. Okay, very different from our mathematical setting here. Also a story about language generation, though. Right, you're trying to generate the slang that you encounter in a new subreddit that you join. And what he and his co-authors found was that when you join a new subreddit or a new online community of the kinds he was looking at first you sound like a newcomer. You use the slang wrong, you just sound ridiculous, right? Like it just doesn't work. Eventually you get used to the community and you're talking just like a regular person in the community. Like you use all the idioms, it's great. But somehow it doesn't persist. As you age in the community, you age there linguistically like you age linguistically in real life. And you start sounding more and more anachronistic. The new slang comes and you don't pick it up. You sound like an old person, right? And so you go through this whole arc of you sound like a newcomer, you're hallucinating idioms that don't exist. There's a moment when you're just right, but the world moves on and now you're... Now, that's not the same as the mechanism here, but it's sort of interesting that generation in our case is kind of working like that. You start by hallucinating and saying wrong things. There's a moment when if you only could stop there, you're just right. But you go through this controlled mode collapse where you get more and more rigid in what you're willing to say. And I sort of imagined, when we wrote this first paper, that like every solution to language generation in the limit must look like this. This is the bargain you're making. Yes, you can generate the limit, but it will always be with this vanishing density. That was somehow my intuition, and my intuition was totally wrong, it turns out. It turns out there's a better algorithm that can generate with positive density. And so I want to use the last 6 minutes to show you how that works. Okay? So this is the theorem, and this is the work with Fan Wei, that there's a constant, positive constant C, so that there's an algorithm that actually can generate an output with lower density that's at least C. And actually, in a subsequent paper that's appearing 2 months from now at Stock 2026, we push this up to basically the best constant you could hope for, which is 1/2. Okay? All right. And actually, okay, so I wanted to just sketch for you how this works. This proof gets very complicated. We're not going to do this in the final 6 minutes. But let me just sketch for you how this works. Okay, so the goal is positive density. The current solution definitely does not achieve that. It moves out to these thinner and thinner languages by design. We have to somehow not do that. Okay, to do this, we're going to first do a detour into, remember we had this notion of index-based generation. And I'm not just outputting elements, I'm actually guessing a language. And what I would like is that eventually I'm a subset of the true language. Let's look at all of my guesses. And let's look at the upper density of those languages in the true language. Okay, so I'm making guesses. Those guesses are enormous infinite objects. They have a density in the true language. What is the sequence of densities that we have here? Okay. So it turns out that any algorithm achieving generation in the limit has to infinitely often guess a language that has 0 density. So in that sense, my intuition was right. Now, remember, this is just the intermediate guess it's making of what the language is. In the end, what we care about is what it said. Right? We care about the words that came out of its mouth out to all time. We want that to be dense. The fact that it's making bad guesses in the middle, we can forgive that, because it has more time. It's going to say more words. But it's an interesting intermediate question. Look at the guesses of the language it made. And it is really true, just like in our critical set solution, that there's going to be an infinite subsequence where it has density going to 0. Here's an example of that. Here's a bunch of languages. Let's say L0 is all finite sets of positive integers. That's a countable size set. And L sub k is the set of all size k sets of positive integers. Okay, so this is the list of all finite sets. We could order it canonically maybe by increasing sum, and these are the things going on. Okay, the sequence of sets, L1, the singleton sets, the size 2 sets, size 3 sets, form what you call a tower whose limit is all the finite sets. Right? Because it's a nested collection of sets that's unioning up to this big set. But each of them has density 0 in the big set. And so the problem is we could end up in the following situation. The adversary is going to output a bunch of singleton sets, long enough that you have to eventually guess it's L1. Because maybe it really is L1. Then they're going to output a bunch of size 2 sets, so you eventually guess it has to be L2. Because all you've seen is size 1 and size 2 sets. Then it'll output a bunch of size 3 sets, long enough that you eventually have to guess it's L3, or you could be wrong. It does this forever. The true answer is going to be L0, and you were wrong infinitely often, okay, as in Gold's theorem. And along the way, you were guessing these sets of 0 density. Now, along the way, you're also outputting actual elements from these things, and maybe that had high density, but your guesses weren't very good. Okay, so that says you're infinitely often generating thin sets. To get this to work, we should also infinitely often be generating thick sets, sets of high density, right? To get this to work, we want to interleave low-density guesses and high-density guesses. How do I get high-density guesses? My current algorithm just recedes out to infinity and is just generating zero-density things. That's not good. So it turns out you can achieve this one stronger thing. Let's say an index-based algorithm for generation is accurate in a given step if its guess is the true language. It lands directly in the true language. Here's a theorem which came as a big surprise to us. There's an algorithm which achieves index-based generation in the limit. So eventually it's always a subset of the true language. And infinitely often, and it's accurate in infinite sequence of time steps. So it's always a subset, and infinitely often it is the actual exact true language. Okay. So it's sort of like Gold's theorem, right? It's getting as close as you can to Gold's theorem, right? Gold's theorem says you have to be correct forever. That's impossible. This says, but what you can do is be a subset forever, and infinitely often be correct. And that's doable. Our previous algorithm did not do that. It receded out to infinity. But you can do that. And in sort of 1 minute, I will give you some intuition for how that works, and then we'll leave. All right. So you're enumerating the strings, and we're going to do the algorithm like we had before. You have these later and later critical languages. And a string comes along. When it belongs to all of your critical languages, you just use the rule from the previous algorithm. Right? So you see a thing like this, it's in all the critical languages, just keep using the next critical language. But then you see a thing like this, where it's not in one of the critical languages. And this gets back to your question about equivalence classes. At that point, it's not in this one, it's not in anything later. So it just destroys that whole chain. That whole chain is destroyed because this string is not in it. And it basically snip the chain, and it goes back to here. At that point, we should guess this one. Okay? The algorithm is now going to guess this. And we're going to start reforming a new chain of critical languages that goes off in some different direction. Okay, so that's the new algorithm. String comes along. If it's in all the critical languages, just use the previous rule. But if it's only in a finite number of them, break the chain and guess this one. Now here's the point. Take the true language. The very next critical language is a subset of it, proper subset. It's missing something that's in the true critical language. That something is eventually going to get enumerated, at which point this thing gets blown up, and the one just before it is the true language. And that will happen infinitely often. So infinitely often we back our way up to the true language, and we output from it. And essentially, if we do this in a controlled way, we can actually generate at positive density. Because we know the infinitely often will back up to the true language. We don't know when that will happen. And when we do that, we output enough strings from the true language that we get to this correct answer. Okay. All right. So let me actually wrap up here. There's a bunch of other things I could say about how this thing works. But the point is, in the end, generation is actually a much more tractable problem than identification. Identification we've known to be impossible for 60 years from one of the oldest results in learning theory. But if I simply change it to I must output valid new strings, I can actually achieve this. And I think there are a lot of interesting open questions here, right? What this suggests is that the actual structure of how this generation happens, right? There are simple algorithms that do it. But you can actually achieve much more. And this idea of breadth and density, I think, is sort of one of the interesting definitional things that come out of this, right? That independent of the abstract model that we're talking about, the idea that I don't just want to generate, but I want to avoid mode collapse, right? I want to avoid a model that just says the same cliches or catchphrases over and over, and that's how it achieves generation. But we actually want to sort of expressively explore the whole space of language. That's the notion of breadth I think would really benefit from more formalization. This is sort of a first attempt at that in a very mathematical sense, but it suggests sort of and hints at a lot of interesting questions and a lot of follow-up work that has happened since then. And I think a lot of interesting things that this community can think about. Thanks very much.
Maybe we'll take one question from the audience.
So going back to your motivating example of parents as the adversary and the infant as the algorithm, so it seems the infant in this case is able to speak all the languages. They just want to speak the language of their parents. So have you thought about reducing the power of the...
Yeah, it's a good question. Right, so actually, right, the infant story, like, in a way, they have access to all languages and they're trying to... So someone who was at an earlier talk about this, afterwards, I saw them like 2 months later, and they're like, I was thinking about the talk, and I realized it explains something about, like, he's like, my child's growing up in a household where we're speaking to them in both English and Hindi. But they only will talk to us in English. And he's like, I've decided what's happened is, one of the languages is English Union Hindi, and one of the languages is English. And they decided that English is sufficient for generation, even though it's a subset of the true language. And so it's enough for them to just generate from English. And how do we convince them to actually generate from the full language, which is sort of a breadth question. So yeah, I think this is actually, this analogy is sort of, like, in some sense the infant is settling on something, even though maybe it actually knows there's a bigger thing out there. I think that it is a very interesting kind of question that does seem to relate to some.
Cool. That's all. Thank you again.
All right, thank you very much.